Okay, so we're going to continue to look at entropy, and entropy is still, I still expect it to be somewhat confusing for you, okay? I understand that. And it's hard to visualize, and you've never dealt with it before, and you're going to start putting numbers on the stuff, and the numbers really aren't going to make any sense. You calculate the entropy, and it's going to be some number with some units, and you're going to go, okay, what does that mean? All right? Keep going with this a little bit, because as we go on, it's going to hopefully become clear why entropy is such an important tool for us, okay? Because what we're going to be able to do is, entropy essentially is not a good thing, okay? Entropy production is generally not good, okay? It means wasted energy, okay? It wasted useful energy, really, okay? Because you can't really waste energy, but you can waste useful energy. And remember what useful energy is, we call it work, okay? And if you have two processes, one that creates a little bit of entropy and one that creates a lot of entropy, generally that low entropy process is going to be more efficient, okay? And so that's kind of the guidelines that we're going to use. Before I get into talking about entropy, I've had a lot of questions lately regarding the first law, kind of going back to that a little bit. And so I kind of wanted to just mention a couple of principles here, okay? Mention a couple of principles. Let's say I have any kind of system here, okay? Okay? And I have some kind of thing going in, some kind of flow going in. That could be water, it could be steam, air, whatever. Nitrogen, it doesn't matter, okay? And I have some flow going out, okay, right? All right? And let's say that in this particular example, you write the first law of thermodynamics, right? Q minus W is equal to M times H2 minus H1, right? M dot, really. And these would be like Q dots, right? Because everything's per time, right? It doesn't have to be, right? You could also divide by M dot and everything would be per mass, right? We've done this a bunch of times. One thing I think people are missing, okay, they're not connecting this to simple energy. Remember that basically the first law says energy in minus energy out is going to be equal to 0 for all steady state systems, okay? Now, the example you had on your homework due last night with that water tank was not a steady state system because that water tank cooled down. Its properties changed, okay? So this equation I just wrote in green doesn't exactly apply to that homework problem because it's not exactly energy in minus energy out on that tank because the tank changed. In that case, it would be energy in minus energy out equals the change of energy of the tank. But in most open systems, in most cases with a control volume, it's what we call steady state, and the properties of the system don't change. Therefore, we can say energy in minus energy out. We're going to be able to write that. If it's a control volume problem, we're going to be able to write energy in minus energy out equals 0 almost all the time. Okay? I think one thing people are not connecting, though, is the green equation to the blue equation there. Okay? They're having a little trouble connecting those two. When I say energy in to a system, it's going to come in the form of like m dot h, like, and how is it going to leave? M dot h. This could be like m dot h1, this could be m dot h2, whatever, right? When you have stuff coming into a system, what's its energy? It's its mass flow times its h. Okay? I think people are not seeing that connection, so I want to make sure you see it. When you have stuff coming in a system, its energy is m dot h. When you have stuff going out of a system, its energy is m dot h. Okay? And then, of course, you have other things that could be coming into the system. Just depends on the nature of the system. For instance, you might have Q in. I don't know. It just depends on the system, right? You might have work out. I don't know. It depends on the system, right? But that doesn't violate energy in minus energy out equals 0. Okay? There's only a few ways energy can go in and out of a system. In fact, the first law that I've written in blue shows you the 3 ways. Heat, work, and flow. Heat, work, flow. Heat, work, flow. Okay? You can bring in heat in and out of a system. You can bring work in and out of a system, or you can bring in flow. You can bring in stuff like air coming in or water, whatever, right? Stuff coming in, stuff going out. It carries energy too. And whatever stuff goes in and out carries an energy of m dot h. Okay? The last thing is, remember that if you have something like H2 minus H1, you can write that as equal to C sub P T2 minus T1 in many cases. I'm going to write below in many cases, not all cases, but in many cases you can write that. You can relate the difference in H's to the specific heat times the temperature difference, okay? And I think that students in thermo tend not to use specific heats a lot, and that's not good because specific heats are your friend. I mean, specific heats make life so much easier. If on the final, just remember this, if on the final you used all specific heats when appropriate and you never used the tables unless you had to, you probably would be able to get almost all the points. You might lose a point because I'd say, well, you'd be a little more accurate if you used the tables, okay? Now, I said use specific heats in many cases, but not all cases. You can't use specific heats when you have a phase change, okay? You can, but you have to account for the phase change, okay? You have to account for the phase change, okay? And see, remember that if you have steam that goes from all steam to all water, it does not change temperature. So according to the specific heat equation, it would look like it doesn't change energy, right? Because if the specific heat equation I have here, if there's no temperature change, there's no energy change, right? But when you don't have a temperature change. So but you do have an energy change, okay? When you have a phase change, if it goes from water to steam, isn't that different energy? Yeah, way different, right? So that's not accounted for in specific heats. Specific heats are only when you're in the same phase. All liquid, all gas, you're cool. Solids, you're good, okay? But we don't do it with a phase change. Other than that, use specific heats a lot. And in fact, remember, whenever you have a liquid or a solid, pretty much all you got is specific heats. That's all you got. Unless you want to use the compressed liquid tables or you want to assume that it's saturated liquid. You know, there's a few little things you could do, but mainly you got specific heats. Yeah.
You have the energy in minus energy out equals 0.
Yeah. Yeah.
What was it? Energy in minus energy out equals?
Stored. Change of energy of the system. But in 99% of cases, we're going to assume the system does not change energy. The only example would be different was that one you had in your homework, which was the one where the tank actually changed its energy because the tank had a certain temperature that changed during the problem. Okay? And so you'd have to account for that. In that case, it would have been energy in minus energy out equals change of energy of the tank, right? Because the tank cooled off. So essentially, you lost more energy than what you put in. When something cools off, it must have lost more energy than what you put in, right? So, okay. Let's talk about entropy. We have three primary ways in which we're going to calculate this stuff called entropy. You can't see it, you don't know what it is, and when you start playing with these numbers, you're not going to know what they mean. But that's okay. That's okay. We'll get there, okay? But I want you to recognize that sometimes students get frustrated and they go, oh, this is confusing. Yeah, it's confusing. It's the second law of thermodynamics. I told you that there's going to be a bunch of you who are going to finish this class and still not really understand the second law. It's kind of weird, but it's kind of true, right? But you better understand the first law. If you don't understand the first law, energy in equals energy out, minus energy out equals energy stored, or if it's flow, you know, it's generally going to be zero. If you don't understand the first law, you can't really pass the class. But you gotta, you know, but you can understand the first law and be hazy on the second law. All right, three ways: tables, using specific heats, and direct integration. We are going to do 1 and 3 today. We're going to use the tables, and I'm going to show you the direct integration. Remember, direct integration, the only thing we're ever going to do in this class, direct integration, is we're going to say the change in S, we're going to assume it's isothermal, means it doesn't change temperature. The change in S is literally just Q over T. That's it. Heat transfer divided by temperature. That's all we're going to say for that one. Yeah. Yes, it has to be absolute. Yeah, anytime you multiply or divide by a temperature, it has to be absolute. Okay, so before we get into the why of calculating entropy, let's go through some examples of actually just dealing with the numbers, okay? Because that's going to be something that we just need to have exposure and experience with, okay? So first thing here, let's start with this one. Here's an example. Okay, we're going back to the old piston cylinder assembly here. We got a piston cylinder, and we got water. Okay? This time it's initially steam, right? It's initially at a temperature of 500 degrees Celsius and a pressure of 3 megapascals, right? Okay. It's allowed to cool at a constant pressure until it's saturated liquid. So the pressure at state 2 is the same as the pressure at state 1, namely 3 megapascals, right? And the other thing you know about state 2 is that it's also saturated liquid. And we got 3 questions. What's the change in entropy of the water? What's the change in entropy of the environment? And how much entropy is produced total? Okay? Now, before we get started, I want you to remember a couple concepts. I want you to recall what I said last time. What I said last time was entropy flows with heat. Wherever the heat goes is where the entropy goes. Okay, that's a really important concept that you need to remember. Where the heat goes is where the entropy goes. Entropy flows with heat, remember? Because entropy is Q over T. So entropy flows with heat. Now look at this piston cylinder assembly. It's initially at a temperature of 500 degrees Celsius and 3 megapascals. Anyone take a guess at what the state of that is? What is it? Is it compressed liquid or what is it? Superheated. Yeah, it's superheated. Yes, anything 500 degrees Celsius is pretty much going to be superheated. So it goes from superheated, which we'll look up in the tables in a moment, right, to saturated liquid. So where does the heat go then? Where does the heat go? This thing starts off as superheated vapor and ends up as saturated liquid. Where does the heat go then? To the environment. So what we're basically saying here is the direction of the heat, everybody hopefully can see this, the direction of the heat is this way, right? It's out. The heat is going out of the piston cylinder. So now that you know, that where heat goes, entropy goes, I want you to answer these 3 questions without numbers. I want you to think of the answer to these 3 questions. What is the change of the entropy of the water? Does the water, what's inside here, go up or down or unchanged entropy? Down. Good. The surroundings. What do you think about the surroundings? Do they go up, down, or same entropy? Up. Good. Then the real question, the third question, what's the total? What's the total amount of entropy? You've got the surroundings plus the insides. You add them up. Is that up, 0, down?
Well, I mean, it can't go down. But
Can't go down. Well, good. We got that one. The increase in entropy principle certainly makes sense. Here's the only way it could be 0 is if it was reversible. If this thing goes from sat vapor down to pure liquid, Would it spontaneously go back to sat vapor, to all vapor? Like poof, there, oh, it's back to vapor, right? That doesn't make any sense, right? So no, this is definitely not reversible process. So we definitely have a positive total entropy produced, okay? And that's all real processes, practically speaking, really have that. Okay, so it's got to be above zero. Yeah. Okay, good. So we got all those three things. Now, how do we do this? This is actually really easy. First part here is tables, okay? So this is the first time we've ever done this. We are going to pull out the tables now for entropy. Here's my tables. And I'm going to go to entropy. I'm going to start out, this is superheated. It is, so my first entropy is going to be my superheated tables for 3 megapascal and 500 degrees Celsius. And I think, hopefully you can see that okay. I highlighted it. That's the entropy right there, 7.2359. Now I don't see the units real clearly, but I'll tell you what they are. So you find it at 7.2359. That's the entropy. That's always the last column in your table, 7.2359. That's the entropy at pressure 3 megapascals, temperature 500 degrees C. So S1 is going to be 7.2359, and the units, if we were to happen to scroll up, would be kilojoules per kilogram K. Kind of weird units. Yeah, it's kind of interesting. Somebody said that in the morning section too. They're like, I've seen those units before. They're specific heat. Yeah, the same units as specific heat. Okay, it's kind of interesting. Remember what entropy is? It's a heat transfer divided by a okay, so that's S1. S2, we look the same thing here. Now we're going to go pressure 3 megapascals saturated liquid. So we got to go to our saturated liquid pressure table. And we got to go 3 megapascals, which is the same thing as 3,000 kilopascals. And we got to go sat liquid. So if we go sat liquid 3,000 kPa, it's 2.6454. 2.6454. And that's same units. Okay. Oh, by the way, I forgot to mention this. We're just going to go and assume that we actually have 5 kilograms of water. That's not really that big of a deal, but I think it's just going to make us the math a little easier. So let's just do it that way. Now let's actually calculate the change in entropy of the water. It's equal to the mass, which I just said arbitrarily, it's 5 kilograms, times S2 minus S1, right? And that's going to be 5 kilograms times 2.6454 minus 7.2359. And this is definitely a negative number. I can't remember what it is. Maybe somebody could do that for me quickly. I don't have my calculator on me, or I would do it.
Negative 22.9525.
How about 22.95? Yeah, minus 22.95 kilojoules per K. So don't ever say entropy can't go down. Entropy can go down for one part of the process. Okay? If you have a process, you always have a process and the surroundings. If you just consider the inside, the entropy could go down. Okay? But if you look at everything, if you look at process and surroundings, the entropy total can't go down. but that's not what's happening here. This is just the inside, okay? The inside said that the entropy went down 22.95 kilojoules per K. What does that mean? You know, that's hard. I mean, that's hard to really understand that, okay, in context, okay? I'll try to give you some better context than the other problems, okay? But in this one, you don't really know what that means. Okay, so then the other thing is, what is the change of entropy of the environment then, okay? Well, the environment, I'm assuming, is going to be at a constant temperature, okay? And it said, by the way, it says here, assume 27 degrees Celsius. So to get the delta S, we'll call it the surroundings, S-U-R-R. If we usually assume surroundings are at a constant temperature, we assume that they don't change. And if we assume something's at a constant temperature, the change in entropy of it is very simple. It's just Q over T. Okay? It's just Q over T, right? Because if as long as it's a constant temperature, you can pull the T out of the integral, and then it's just Q over T. Okay, so in fact, I'll even make this easier. The temperature is be Q divided by the temperature, and the temperature is 27 degrees Celsius, but you have to put it in absolute, right? And so it turns out this has to be 300 K. All right, so as long as I can figure out the heat transfer, into the surroundings, I can get the change in entropy of the surroundings. Okay, so how am I going to figure out the heat transfer into the surroundings? Well, that's the same thing as the heat transfer out of the piston cylinder assembly, right? So how am I going to get the heat transfer out of this piston cylinder assembly? What are you really saying? I mean, you're saying look up the H's, but what are you really saying? How would you explain that at the beginning? I mean, you explain this, do you just say, oh, look up your H's and you're done? No, what you're doing is the first law. You do the first law. Yeah, I mean, you're saying that practically you're saying look up your H's, but you're really saying follow the first law of thermodynamics, right? Remember that the only way practically to calculate Q is the first law, okay? Remember I told you that? I said really the only way we have to practically calculate Q is the first law. So if you ever see an example where I ask you to calculate the heat transfer, all you got is the first law, all right? Q minus W equals change in H times M, right? That's really all you got. Now, I will mention this, though. I suppose there is a way that if somehow you could figure out the change in entropy, you could then get Q without doing the first law. There might be a way, because look at this equation, right? If somehow I knew the change in entropy, and I know the temperature, couldn't I use that equation to solve for Q as well? We don't know the change in entropy. I'm trying to solve for the change in entropy. I need Q, and the only way I know how to solve Q is first law. That's all I got, okay? Now, remember this. For the piston cylinder assembly, okay, remember, that's actually a closed system. So really, for closed system, it's going to be Q minus W equals M U2 minus U1. But remember that when you bring over the W to the other side, you're really saying this, U2 minus U1 plus W. But since it's a constant pressure process, you're saying M U2 minus U1 plus the mass times pressure. Remember this, if it's a constant pressure process, the work is just P times V2 minus V1. And then, remember this, H is equal to U plus PV, right? And so you can then simplify this greatly and actually say that, okay? Which some of you have been doing for weeks, but others of you still are kind of going, what is that again? That's okay, though. That's okay. Because honestly, if you want to, you can just keep this second to last line and calculate everything. Okay? If you can't see this. But you can do this last little trick here only when you have a piston cylinder assembly. Yeah.
I can't tell, is that a specific volume?
Yeah, those are specific volumes. This has to be, since I have mass on the outside, I have specific volumes on the inside of that parentheses. V2 minus V1 are specific volumes. Okay? So what this implies basically is what was already offered, and that is if I want to calculate the Q, the heat transfer, it's going to be the mass times H2 minus H1 in this case. Or if you don't like that, go back and do the internal energies and do what I did, you know. If you don't like that, just do this. Do the second to last line there. Do the second to last equation. But I'm going to simplify it and do that final equation there. So all I have to do real quick here, and I'm just going to, in order to save some time, I'm going to do this fairly quickly. To get H2 and H1, how am I going to get H2 and H1? I'm going to do the same way I got S2 and S1. Look them up in the tables. It turns out H1 is 3457.2 kilojoules per kilogram. And it turns out H2, if you look in the tables, is 1008.3 kilojoules per kilogram. Okay, so that's just straight up from the tables. H1, H2, straight from tables. Okay, just straight from the tables, that's what H1 and H2 are. So in order to solve for Q, you plug in those values of H1 and H2 into that equation there. I'll do it here so you can see the numbers again. 5 kilograms times H2, which is 1008.3 minus H1, 3457.2. And what you get, by the way, for Q is equal to minus 12,245 kilojoules. Okay. Look them up in the tables. H's were in the tables. Because you know everything about state 1 and state 2 in this problem. Remember, we use the tables to get entropy. If you can get entropies, you can get the enthalpies, right? If you can get the S's, you can get the H's, right? I mean, so you just look them up. So, okay, now here's a question for y'all. I think you can get this one, right? Notice that Q is negative. What was I doing, and why is it negative? Why is it negative? Because it's coming out of what? Piston cylinder assembly, right? I did an analysis of this piston cylinder assembly. It was negative coming out. But if it goes into the environment, what's that sign going to be? Positive. So when I look at this equation that I have for Q divided by 300K, the Q is going to be the same number, but it's going into the surroundings. Therefore, it's not going to be negative. It's going to be positive because it's going into the surroundings. So that actually is going to be a positive 12,245. So if I do this, I'm going to write 12,245 kilojoules divided by 300K. Somebody give me that number. It's like 40.8. I think we'll go 40.8 or whatever, 40.82, whatever, something like that. Okay. Notice I'm going to circle these in green or square. That is the entropy change of the water. This is the entropy change of the surroundings. Oh, whoop, sorry, yeah, you're right. Just making sure you're paying attention. Kilojoules per Kelvin. There you go. Yeah. I'm going to scroll up so I get a little more space here at the bottom. Here's what we're effectively saying here. This is very simple here. The entropy change of the water plus the entropy change of the surroundings is equal to what we call the entropy generated. This is where it just kind of comes from nowhere. Poof, there's entropy. Okay? It turns out in this case, if you calculate it, pretty simple here. You get your calculator and you take 40.82, which is the surroundings, and you subtract off the entropy change inside of the water, which is 22.95. You get 17.87 kilojoules per K. It's positive, which it should be, because you've always got you've always got some entropy produced, unless it's zero and it's a reversible process. That would be like perfect. That would be the best possible. Okay? All right, let me go through this next one. I'm going to have to go through kind of quick. It's kind of doing the same stuff as what we already did, but I want to just go through it real quick. Because I don't have a lot of time. We've got to kind of move on this and at least get this done pretty quick. So here's what we got. A room contains two condensers. One which condenses steam at 250 degrees Fahrenheit and another which condenses steam at 120 degrees Fahrenheit. Assume the room temperature is 80 degrees Fahrenheit. I wanted to do a problem with English units. Which process is more reversible? Calculate the entropy produced with each process. Okay? Which process is more reversible? Okay. So here's what we're going to do. There's a couple things I wanted to show you with the second example. Let me just kind of give you the visual here. Let's just say you got a room, it's got air in it, and it turns out this air is 80 degrees, okay, Fahrenheit. So fairly warm room, but not crazy, right? And inside the air, we're going to condense steam. So what we're going to have here is heat transfer Q is going to come in from the condensing. Now when you condense, what are you doing? No, but what are you practically doing? What's happening to the stuff? It's the steam. What's happening with the steam? It's cooling down. It's losing energy. But what practically is happening? It's not pressure, but what's it doing? Like if you were looking at the steam condensing, what would it look like? No, just looking at it. It would take it from steam to water, right? Right? You on a hot summer day, and you have a glass of pop or whatever, right? A cold liquid. What happens to the surroundings of the glass? Water condenses on the glass, right? If on a cold winter day, sometimes you'll see this on the inside of your house, you'll have water condensing on your windows, okay? What condensation practically means is you're going from vapor to liquid. That's all it means, okay? So when we say condenses steam, what that's saying is it's taking it from saturated vapor to saturated liquid. That's all it means, okay? That's all it means. That's what condensation is. You're taking it from vapor to liquid. Saturated vapor to saturated liquid, okay? Now, it says it condenses steam at 250 degrees Fahrenheit because when you condense something, you're changing phase. Remember that, right? You're going from vapor to liquid, right? When you change phase, you don't change temperature. When you change phase, you don't change temperature. That whole thing is always 250 Fahrenheit, okay? So let's just get practically what this means. The change in S of the steam that's condensing, how do I get that? No, I don't have any masses here, so everything's going to have to be per mass. Okay? I can actually do this two ways. First, I can use the tables. Certainly can use the tables. Okay? That's what I'm going to show you first. Obviously, if you can use tables, why would I ever show you another way? Just because I want you to learn. Let's go to the tables. Okay. Now this is English units, so I got to go to my English tables. And this is going to be saturated water temperature table. Good. Now here's where I'm at. I'm at 250 degrees Fahrenheit, if you can read that from here. Maybe I can make it bigger. Okay, that's a little bit bigger. Can we still get it all on the page? I think I can, yeah. That's 250 degrees Fahrenheit. That's where I'm at. Now, the last three columns here, that's the entropy. You probably can't see it, but it's sat liquid, evap, and sat vapor. The evap term is basically what you're doing, right? because the evap term is the difference between sat vapor and sat liquid. But that's what condensation is. Condensation is going from sat vapor to sat liquid. So the change in entropy that we have here is just this number, 1.33216. And the units this time are BTU per pound mass Rankine. So you can get this from the tables pretty easily. 1.33216 BTU per pound mass Rankine. I mean, obviously that's really easy, okay? Again, to remind you, that's just the evap term for entropy at a temperature of 250 degrees Fahrenheit, 1.33216, because that's condensation. Oh, by the way, that's really negative, right? Because the change in entropy is going down, right? Because I went from sat vapor to sat liquid. So I lost entropy, right? Okay, here's the other question then. There's another way I can do this. I just thought it'd be interesting to show you this. There's another way I can do this, and it's actually kind of helpful for the other part. The other way I can do this is I can say this. The change in entropy of the steam is equal to, hold on a second here, Q over T. Why can I use this? Why can I use Q over T in this particular special case? What has to happen when you use Q over T?
Yes,
Constant. But when you condense steam, I just told you that it doesn't change temperature. So this works in this special case. When you condense steam, the temperature does not change. So now, what's going to be Q? Well, the only way I can solve for Q is the first law. Now, the first law for this process is very simple. Remember the first law, Q minus W is equal to M H2 minus H1. But in this case, I don't have any M's, so I really have Q minus W equals H2 minus H1. But then, if I want to, there's no W in this case, right? There's no work. Condensation doesn't produce any work. So simply, if I want to solve for Q here, it's simply going to be H2 minus H1 over T. That's all it's going to be. And of course, this is per mass. Per mass. Now, that's easy. From our tables, that's easy, right? Go back to our tables here. H2 minus H1 would be the evap term again. Because remember, I'm going from sat vapor to sat liquid. So H2 minus H1 is the evap term. And at 250 degrees Fahrenheit, the evap term looks to me like 945.41. 945.41. So that's going to be equal to 945.41 BTU per pound mass divided by the temperature. The temperature of steam is 250, but you can't put 250 in there. You cannot put 250 Fahrenheit, right? You've got to put in absolute. So that's 250 plus 459.67. So you're really putting in 709.67 Rankine there. If you do the calculation, oh, and by the way, H2 minus H1, this should really be negative because, again, it goes down, right? The heat transfers out, right? Heat transfers out. This thing condenses, it loses heat. So that really should be negative. So you get the same number. If you check it, you get the exact same number. Which is cool. That's kind of interesting. So get the same number. It's not different units. Yeah. It's only because I had a constant temperature. Normally, if you have a phase change, or if you don't have a phase change, if your temperature is changing, you can't just always write this. In fact, the second part there, this statement, whenever you write change in entropy Q over T, you have to be careful. Make sure that's a constant temperature process. If it's not, that's garbage. Okay? So I didn't show you this second part because I practically thought that's what you'd use. I show you that second part to hopefully connect the concepts. Go, oh, wow, that's the same thing. That's kind of interesting. It's the same thing for that case. All right. So one more thing here. Let's do, that's the change in entropy of the steam, right? I want to do the change in entropy of the room, which actually is going to be really easy in this case. The change in S of the room is going to be the Q over T of the room. But I've already calculated the Q of the room, right? Because whatever is lost from the steam goes into the room. And I've already calculated. It's that 945.41 BTU per pound mass. But the temperature is the temperature of the room, which is 80 degrees Fahrenheit, right? So 80 degrees Fahrenheit plus 459.67 is 549.67. And now if I do the division here, 945.41 divided by 549.67, you get 1.72 practically BTU per pound mass Rankine. So what's the total entropy produced? What's the S produced? Or the S, I guess I've been calling it S generated. Your book says generated. The S generated is equal to the change in entropy of the steam plus the change in entropy of the room. I'm going to call it the room. Okay? So that's going to be that minus 1.332 or whatever. So it's about 0.39 BTU per pound mass Rankine. Okay, practically here we're running out of time because we got to do a quiz and still do some other stuff. Let me just leave this with you. I'll leave this here. But let me tell you, if you were to redo this analysis with the other temperature, which is the lower temperature steam, what's going to happen is that your S-gen is going to be much lower. You're going to generate less entropy with the lower temperature steam because you're having transfer from two temperatures that are really far apart. That's less reversible. Okay? So I challenge you to do the other one. I believe that the other one will be an S-gen somewhere around 0.05. I'm roughly remembering something like that. So try it, see it, okay? Do it. It's the same numbers. The only thing you have to do now is look it up for 120 degrees Fahrenheit, not 250. Everything else is exactly the same. But you will definitely get less S-gen.